Electron dot structures are a simple diagram that shows us how many valence electrons an element has. Now, why would we care how many valence electrons an element has? Well, in my chemistry class, my high school students begin to realize that the number of valence electrons is one of the most important things that we will ever learn in introductory chemistry. Because when an atom bumps into another atom, what's the first thing that bumps into each other? It's not the nucleus. It's not all the electrons. It's just the electrons on the outermost edge. So if we can understand how many they are and how they will interact with other atoms, boy, this is a huge leap in our understanding of chemistry. Now here's a disclaimer. Electron dot structures are also called Lewis structures, and you'll hear me call them both. And when you read textbooks or you watch other videos or you read a question, it'll have all of those included because they're both used. They mean the exact same thing. I'll try to remember to say electron dot structures, but sometimes I'm just automatically going to say Lewis structures, and they mean the same thing. Now, look, there's a box on the screen. If there's a box on the screen, you need to write this down. These are the step-by-step instructions for how you write these very simple electron dot structures. We're going to expand on this in some later lessons, and we're going to draw much more elaborate structures, but this is a good starting point. Now, you need to remember that the electron dot structure is just showing the outermost or the valence electrons. So how do we figure that part out? Well, there's an earlier lesson to walk you through that. If you need to go back there, look in the description and you can find it. But we write out the electron configuration and we determine the number of valence electrons. Then we put a symbol in the center. You can see that with the chlorine there. The chlorine is the Cl in the middle, and then the dots around the outside are the valence electrons. So we put the dots around the outside. The rotating thing, I'll show you what that means. Each dot represents one valence electron. They don't pair up until they have to. What do we mean by that? Well, that goes back to the rules that govern where electrons live, and we're just representing that by some of them have an electron near them and some of them don't. Now, it doesn't mean chlorine wouldn't like to have an electron, so maybe it would find a friend and they could share an or steal an electron. But I'm getting ahead of myself. And the valence electrons are the electrons only at the highest energy level. One thing to remember, as electrons are filling up, the first energy level can only hold 2 electrons. And if an atom only wants the first energy level full, then 2 electrons would make it full. Every other energy level after that holds 8 electrons. They're not filled until they have 8 electrons. When you're done writing that down, let me walk you through what all of this means. We've got sodium up here on the screen, and I've already given you the electron configuration for sodium to try to speed up the process and really help you understand how this works. So we need to know the electron configuration to figure out how many valence electrons it has. In this case, we look for the highest energy level where electrons are living. That's the 3rd energy level. The s orbital, there's 1 electron. So sodium has 1 valence electron. Look at there. We've done number 1. Number 2, write the element symbol to represent all inner electrons and the nucleus. So we've got sodium, Na. That represents all of the electrons. That's these right here that we are not representing because they're just hanging out in near the nucleus. And we're only concerned about this one guy that's living way out there. So we've done number 2. Then we're going to put dots around, rotating until we've used them all up. Now this one's pretty simple, right? Because look, we have 1 valence electron to use, and there's our sodium. So we'll put 1 valence electron. And this is the Lewis dot structure or the electron dot structure for sodium. Let me clarify a couple things. I put the 1 electron right here, but it doesn't have to be there. I could have put the 1 electron right here, or I could have put it right here, or I could have put it there. As long as I'm just showing 1 valence electron, that's perfectly fine for now. Next up, aluminum. I've written out the electron configuration to speed this up a little bit. So we need to determine the number of valence electrons from this. We're looking for the highest energy level. Oh, I see the 3rd energy level here and the 3rd energy level here. There are 2 electrons in the s orbital in the 3rd energy level and 1 in the p orbital. That's a total of 3 valence electrons. I'm going to write the element symbol, which is aluminum. I'll put Al right here. And then I need to add electrons or dots around the outside. Okay, we have 3 to be able to put on here. I'll put 1 here. I like to start there, and then I work my way around. Now the thing is, I'm going to make a mess of this up here, but I want to show you. Electrons will either live here, 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 or here when we're talking about valence electrons. It's just our way with electron dot structures that we represent this, and it's going to be very valuable later on when we start building larger compounds with our electron dot structures. So I'll just start right there. There's one electron. Now I'm not going to put the second one there because remember, they don't pair up until they have to. So let's go over here. There's 2. Now I'm not going to put one next to it, and there's 3. So I've put 3 electrons around my aluminum, and that's how many I need. That's it. That's all you have to do for the electron dot structure for aluminum. I think we're at a good spot to put together all the things that we've learned up to this point about electrons, electron configuration, valence electrons, and electron dot structures. And if we can put all those together, it really shows our understanding of all these topics that we've learned. We're going to start with sulfur. First thing we need to do is find sulfur over here on our periodic table. It's very small, but there it is. It is number 16. So it has 16 electrons as long as it's not an ion, as long as it's electrically neutral. First thing we need to start with is the electron configuration. We do that here with what I call my electron ladder. And I'm going to start to put 16 electrons on here until I've filled it up. I've used up 2 electrons there. I've used up 2 more electrons here. The next 6 and 2 can go here. That's a total of 8 electrons. Ooh, I made a mistake. Let me fix this. This should be 4 because I'm keeping track of how many I used. So there I've used a total of 4, and then I put 6 here and 2 more there. That gives me a total of 12 that I've used up. I'm glad I caught that. And I have 4 more. Those are going to go here in the 3p. So let's write out the electron configuration. 1s2, 2s2, 2p6. I'm right here. 3s2, 3p4. Now, just for practice, we want to see if we can turn that into the noble gas configuration. Way we do that, we come back here and find sulfur, and we work our way backwards until we reach a noble gas. Look, here's neon right there. Neon is number 10. So neon, 6, 7, 8, 9, 10. Neon has this electron configuration. I'm going to put it down here as Ne. Then I'll write everything that's left because that's how we do noble gas configuration. We just did this one. Now the electron dot structure, the way I do that, I first need to figure out, well, how many valence electrons does this have? I can do it from either one of these, right? Because here's the third energy level. There are 2 electrons there and 4. That's a total of 6 valence electrons, V, E negative. And down here it shows the exact same thing, third energy level, 2 and 4 there. That's 6 valence electrons down here. So I need an electron dot structure or Lewis dot structure with 6 valence electrons. I put S here because that's my elemental symbol for sulfur. And then we're going to go ahead and put 6 valence electrons around the outside. 1 there, 2, 3, 4. Notice none of them paired up yet. 5, 6. I cannot stress to you how important it is for you to do these on your own. Here's what I would do. Pause the video, work through all these with iodine, make sure you can do them on your own, and then turn the video back on, check your answers, and now you won't need me every time you need to do these because you're proving to yourself you can do them on your own. Look, this is a lot of electrons to write out the electron configuration for, but we got this. I'm going to write them out in the order that they filled up. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. And for practice, the noble gas configuration, there's iodine. Let's work our way backwards until we find the noble gas nearest and lowest in number. That's krypton. And krypton is number 36. So just to show you on here, 2 more is 4, 6 more is 10, 2 more is 12, 6 more is 18, 2 more is 20, 10 more is 30, trying to get to 36, and right here that makes 36. So krypton has 36. We'll put Kr here, and then I'll write the remaining 5s2, 4d10, 5p5. Good, noble gas. Next one we need to do is electron dot structure. To do that, we need to know how many valence electrons. I can look at either one of these, but let's just go to our noble gas. Look, I've got 5th energy level and 5th energy level. Why aren't they in order? Because they didn't fill up in order. But we're looking for the highest energy level. We can see it there. And how many? We have 7 valence electrons in that energy level. Okay, well, let's draw it out. 1, 2, 3, 4, 5, 6, 7. Did you get it right? Did you get it right on your own? I hope so. And if you did, this is really good because you had to learn a lot to be able to get to this point. We're getting to the point in chemistry where every time we have these nice set of rules that kind of explain how things work, there are always exceptions to the rules because electrons and atoms, they just don't seem to care about our rules. We learn about the rules to help us learn about chemistry. As we learn more about chemistry, we need to understand, okay, sometimes it doesn't work perfectly as we would hope and doesn't follow our rules exactly. I just want to show you this as an example. That's why we're not writing this down. You don't need to have this in your notes. We're going to go over this thoroughly later on. But we need to increase our understanding. We need to expand what we really know before we can truly understand why these are happening. Here's titanium, right? Titanium's electron configuration is on the screen, and then I've got the noble gas configuration over there. How many valence electrons does titanium have? It'd be really easy to look at this titanium and say it has 2 valence electrons because the 4th energy level is the highest energy level and it has 2. Turns out it actually has 4. Now here's the frustrating thing, and I tell my students, do not worry about this exception. You stick with everything we've learned up to this point, right? If you were to answer this question on a test in my class, at this point in our learning, you would tell me that titanium has 2 valence electrons because that's what you have learned. We have to learn some more things to understand, okay, when do I deal with this exception? So I don't want to frustrate you at this point. I just want you to understand that this is going to become more complex. For now, you don't need to worry about the complexity of it. You just need to answer everything as normal, and you're going to be super successful as we progress. Well, we've learned a lot up to this point in our chemistry, and there's a lot of things on the screen that'll help you out and take you to learn more things. I also want to encourage you to come over to my other YouTube channel, which is Beals Science, because I've got all of this stuff we're learning about as experiments and demonstrations and applying it to real life. Or you can come over to bealsscience.com and you can see everything that I've got going on in the science world. And I do all of this just to remind you to keep on learning.